Hi, it's Mr. Mac, and in this our 8th video in the series Maths Skills You Need, we're going to be looking at surface areas and volumes.
This is Mr. Mac. He can explain things really well and is a lot of fun to watch. You can subscribe to Mr. Mac's Physics channel. You will find mathematics problems, science demonstrations, astronomy and space pics, physics calculations and simple explanations of advanced concepts.
We're looking at surface areas and volumes, and here you can see I'm holding up the lighthouse at Kiama on the south coast of New South Wales. Obviously it's leaning and I'm saved the day. On the left hand side you can see I've made a three-dimensional drawing of that lighthouse just to simplify things. And if we were asked to paint the outside, that's beautiful white there, then we could calculate the amount of paint we needed and the cost. What are we learning to do? We're learning to calculate surface areas and volumes of three-dimensional solids. We'll be able to apply formulae to prisms, cylinders, spheres, and composite solids like the Kiama lighthouse. Let's have a look at the surface area and volume of a prism. Now, a prism has a cross-sectional area. In this case, if you look at the bottom of the screen, you've got a triangular prism, and the triangle is shaded red. And if you sliced that prism with an imaginary knife parallel to that red triangle, then every time you slice it, it'll look exactly the same in its cross-section. And that's sort of a quasi-definition of a prism. When we're finding the surface area of a prism, in this case we want twice the cross-sectional area plus the areas of the other sides. So in this case we wanted two triangles plus a rectangle on the bottom, rectangle on the left, and the sloping rectangle that's facing us. And we can substitute for formulae that we know, because the area of a triangle is a half base times height. The area of a rectangle is length times width. So we just replace those. And we'll substitute the numbers that are there. So for the triangle, the base is 2 centimeters, the height is 2 centimeters. So it's 2 times a half times 2 times 2, plus the bottom rectangle is 5 centimeters times 2 centimeters. The back or left rectangle is 5 centimeters times 2 centimeters, and the sloping rectangle, the one that's sort of facing us, is 5 centimeters times 2.8 centimeters, which gives us, and you could probably do this in your head, but use a calculator to be safe, 4 plus 10 plus 10 plus 14, which is 38 centimeters squared, remembering that the units are squared because it's an area. The volume of a prism is the cross-sectional area times its height. Now, that height doesn't necessarily mean how high it is, but the perpendicular distance going along. In this case, h is 5 centimeters. So the volume of a prism is simply a times h. In this case, the area of the triangle that's shaded is a half times 2 times 2, and the height is 5 centimeters. Multiplying those together, we get 10 centimeters cubed. The units, of course, for volume is cubed. Now imagine that we want to find the surface area and volume of an irregular prism. So we don't have a nice neat triangle or rectangle or hexagon or anything that we can find easily. We've got this irregular shaped swimming pool, and it's made by having a kidney shaped wall that's made out of plastic that stands, and there's a base that's the same shape all the way up, that sort of kidney shape, and it's filled with water. Now we would like to find the area of the materials that we need. So the darker blue, this area of the side we're given is 10.2 meters squared, and the area of the base we're given is 12.7 meters squared. So how do we find the surface area? We simply add those areas, remembering that this time there's no top on the pool, so we don't have to add twice that cross-sectional area. The base is the cross-sectional area, and if you look at it anywhere horizontally, the pool is the same shape. So we want to add the area of that kidney-shaped base and add that with the area of the side, which, if you can imagine it was cut once vertically, you could stretch it out to be a very long rectangle, and so it should be easy to find. In this case, we're given the numbers 12.7 plus 10.2, which is 22.9 metres squared. But what about the volume? We want to fill up the pool with water. How much water do we need? Well, it's simply area times height, as we found out in our last example. So in this case, it's 12.7, the area of the base, times 1.2, the depth of the pool, assuming we're filling it to the top, which is 15.24 metres cubed. So that's how much water we would need to fill this pool. Well, what about a sphere? Let's find the surface area and volume of a sphere. Here you can see a diagram of a sphere that is 15 centimetres in diameter. Now that would be the equivalent of a foam ball that you could buy from Spotlight or other crafty stores. And of course, knowing the diameter, we halve that to get the radius of 7.5 centimetres. This, by the way, is also useful if you wanted to do a scale model of the solar system, because it would be a 1 to 10, it would be 1 to 1 trillion scale, and you could hold that up and as the sun, paint it nice orange or red or whatever, yellow, and pace out where the planets lie and how big they are. On that scale, Jupiter would be the size of about a marble. Anyway, let's find the surface area of this foam ball. It is, of course, the area is a different formula. It's 4 pi r squared, which is 4 times pi times 7.5 squared. In this case, using a calculator, it's 706.858, and the digits keep going, centimetres squared, which we can round to 707 centimetres squared to 3 significant figures. And what about the volume? The volume is a new formula. It's 4/3 pi r cubed. So 4/3 times pi times the radius cubed, which is 7.5 cubed. And again, using calculator, we end up with 1,763.480, and the digits keep going, in centimetres cubed, which to the nearest centimetre cubed is 1,763 centimetres cubed. So we have a cylinder here, and we want to find the surface area and volume. You can see that the radius is 2 metres and the height is 5 metres, so you can imagine this could be a real-life example of a rainwater tank that sits beside a house, perhaps on a rural property, and it's covered over on the top. It has obviously a bottom, so we need to find the surface area of the metal that we need and the volume of water that it can hold. The surface area of a cylinder is found by twice the area of the base plus the area of the side. Now the side, that's the darker red. If you imagine again cutting it from top to bottom and stretching it out, flattening it, it'll become a rectangle. The length of that rectangle is the same as the circumference of the circle on the top. The width of that rectangle is the same as the height of the water tank or cylinder or whatever. So in this case, we simply go twice times pi r squared plus 2 pi r, that's the circumference, times h, the height. And that second part, 2 pi r h, finds the area of that rectangular side. In this case, we're substituting, so 2 times pi times 2 squared plus 2 times pi times 2 times 5, which gives us 87.964, and the digits keep going, centimetres squared. Rounding that to 3 significant figures, you'll notice that the 9 rounds up, carries over, and the 7 also goes up to 8. So we have 88.0 centimetres squared correct to 3 significant figures. That's how much metal we need to make a rainwater tank this size. How much water can it hold? The volume is similar to our prism because in a sense it's a circular prism. The circle at the bottom is the cross-section all the way up, and the height is its vertical height. So pi r squared h. In this case, pi times 2 squared times 5, which is 62.831, and the digits keep going, in centimetres cubed. Rounding that to 3 significant figures, we have 62.8 centimetres cubed. What happens when we have a composite shape? Now, this composite shape is a very real example. You can imagine going to a sporting shop and buying 3 tennis balls in a cylindrical container. And we know that the diameter of each tennis ball is 6.7 centimetres, and we can work out then 3 times that is 20.1 centimetres as the height. We have everything we need to know to find details about this carton of 3 tennis balls. And the question we want to find is, what's the volume of air inside? So we know that the tennis balls are sitting touching each other, but there's a lot of wasted air. So what is that volume? Well, in this case, if we look at the diameter as 3.7, we need to then quickly work out that, dividing by 2, the radius is 3.35 centimetres. We need that for the calculations. The volume of a sphere, as we saw before, is 4/3 pi r cubed. So we substitute, so 4/3 times pi times 3.35 cubed. And that turns out to be 157.479, and the digits continue. And so the volume of the cylinder now, that's the red part, is, remember, it's a prism, it's a circular prism, so it's area times the height, so pi r squared times h, and again we substitute and we get pi times the 3.35 squared times the height of 20.1, and we find out that that's 708.656. And so the volume of air is found by subtracting. We get the volume of the cylinder, which we just found, and we take away 3 tennis balls, so it's 3 times 157.479. And we find that the volume of air then, by doing the calculation, is 236 centimetres cubed, correct to 3 significant figures. Well, let's get back to our Kiama lighthouse. The diagram that I've put on the right-hand side is a simplified version of it, with some of the details of the diameters and heights of 3 different sections. And you can see that if we were given the charge of painting the exterior of the lighthouse, then we would have to do some calculations. These diameters, by the way, are very easy to find just by measuring. Same with the heights. So we're also given the information that 1 litre of paint will cover about 6.5 metres squared of a wall. And once we know the diameters, we can calculate the radii. So radius 1 at the top, the smallest part, is 1.6 metres. Radius 2 is 2.32 metres. And radius 3 at the bottom, the base of the lighthouse, we've got 3.46 metres, just by dividing by 2. And let's paint it pretty colours. Why stick with white when we could paint it green and red and blue? Well, that's going to be a key for unlocking how we calculate this. So the blue is a circle, quite clearly. You can see it as that drawn in perspective. The green, as we know from the side of any cylinder, is a rectangle. And so we have 3 of them. And the red, each one's called an annulus. An annulus is a circle with a smaller circle cut out of the middle. and we can calculate the areas of each of those. And set it up so it's easy to follow. So I've done this with colours, matching the colours we're painting it. The area of the circle at the top, the surface area, plus the area of the annulus at the top, the annulus at the bottom, plus the 3 rectangles, the top, middle and bottom. The surface area of a circle is simply pi r squared, and the radius in this case is the very first one. For an annulus, we can use this funny formula that's pi brackets r2 squared minus r1 squared, close brackets. And we need that for the 2 different sizes. And then we've got 3 rectangles. And each rectangle, the circumference of the circle times the vertical height will give us the area. So 2 pi rh will find us the area of the first, second and third rectangles, which are the sides of the lighthouse. So let's substitute. We have everything we need. So for the circle, pi times 1.6 squared. For the small annulus at the top, pi brackets 2.32 squared minus 1.6 squared, plus the annulus at the bottom, pi times brackets 3.46 squared minus 2.32 squared, plus the 3 green sides or rectangles, so 2 times pi times 1.6 times 1.82, plus 2 times pi times 2.32 times 13.68, plus 2 times pi times 3.46 times 2.42. And we can do that in one step on the calculator if we're careful, or we can do it bit by bit and add them together. We should get an answer of 307.930, and the digits keep going, in metres squared, or 308 metres squared to 3 significant figures. And we do need that because we want to work out the amount of paint, and we're told that 1 litre of paint will cover 6.5 metres squared of a wall. So let's divide that surface area by 6.5, and we find that we need 47 litres of paint, approximately. And let's also work out the cost. The cost of paint is approximately $20 per square metre. So we multiply the amount of area times $20, and we end up with $6,160 approximately. And there's a practical application of surface area of a composite shape. So we've seen how to find surface areas of some 3-dimensional figures and the volume of some 3-dimensional figures. In our next video, we'll be looking at areas of circles and sectors of circles and having a few more complex problems. I'm Mr. Mac. Thanks for watching.